Welcome to this presentation and thanks for having me here. I'm Nele Mentens. I'm a professor at Leiden University in the Netherlands and at KU Leuven in Belgium. And this presentation will be about the research that we did in the past years on the security of flexible electronics on plastic substrates. So this is the outline of the talk. First, I'll say something about the technology. Then I'll briefly introduce what we need to make, in terms of hardware, to make a secure system. And then I'll touch three topics: crypto circuits, key storage, and random number generation in the technology that we used. And I'll draw some conclusions. So first of all, flexible electronics on plastics have been used for many years, and there's widespread commercial use in flexible displays. And in these displays, millions of thin film transistors are controlling the current through the pixels in the display. Now, some years ago, like 5 to 10 almost years ago, researchers started noticing that it was also possible to make digital circuits in this technology. And there, the challenges are much larger to have. I mean, we cannot have millions of transistors there yet, like in the displays. But it turned out that it's possible to also make circuits or digital circuits in this technology. And there's actually a large potential for flexible digital circuits in passive RFID or NFC chips that are integrated in plastics or in paper. And the reason is that these chips are bendable, stretchable. And examples are flexible labels, as you can see on the pictures, intelligent packages, smart blisters, or electronic medical patches. Now, a number of circuits have already been fabricated and shown to be fully operational. And examples are like an NFC transponder, 8-bit microprocessor with a limited instruction set, be it, but still. And you can see some examples also on the pictures here. Now, which technology is mainly used? There's actually several technologies that are used, but the one that shows like the best combination of high performance and low processing costs is amorphous metal oxide. It's based on amorphous metal oxide thin film transistors. And you can see a cross section of a transistor here and the connection actually of via. Where you can see that the substrate is plastic, like we said before. The semiconductor is amorphous indium gallium zinc oxide, or AIGZO. The gate dielectric is silicon dioxide. And then both the gate metal and also the metals, the metal wires and also the via are made in molybdenum. So why would we use this technology? This is a comparison with some ballpark numbers, let's say, and on the left side, I put silicon technology with a feature size of 10 nanometer. Then the middle column shows the technology that we used for our first experiments that I will present later. And on the right side, you can see AIGZO technology in new generation. Actually, this is already commercially available also in the meantime. So the first thing that you can see is that the core supply voltage in silicon technologies is much lower than in the technologies that we use. So which among other effects will lead to a higher power consumption. And this is of course a negative effect. Then the charge carrier mobility is also a lot lower, which will lead to lower performance. Then when we look at transistor density, this improved a lot in the new generation already compared to the generation of the technology that we use in our experiments, but still the transistor density is a lot lower than in silicon technologies. So flexible chips on plastic substrates typically have a larger area. Then when we look at the semiconductor type, in silicon, we can have N-type and P-type transistors. In the technology that we use, in this AIGZO technology, there are only N-type transistors. So we need to use unipolar logic in our standard cells. which can have an effect on the reliability, for example. So that's, again, a negative. So why would we use the technology then? And the main reason is that the cost is a lot lower. So, and this has to do with the fact that the fabrication process can be done at a much lower temperature than in traditional silicon fabrication processes. So the cost per 1,000 transistors is, as you can see in the slide, significantly lower than in silicon technologies. Another advantage, depending on the application, of course, if it's necessary or not, is that the chips are flexible. So they are bendable, stretchable, and this also makes a difference, of course, for some applications. So of course, there's a lot of disadvantages and only a few advantages. But yeah, where this technology is interesting is, of course, for those applications for which cost is super important, and also this flexibility is super important, and where the other factors that are shown here on the slide are less important. So we mainly focus on those applications, and I already showed a few on the previous slide. And when we assume that these applications really benefit from the advantages that are shown here, then of course it makes sense to take a look at applications or at chips made in this technology. So we already said something about digital circuits in the technology, and also about advantages and disadvantages. Now there's one more thing that you need when you want to make a digital chip, and that's non-volatile memory. Especially when we will look later at cryptographic chips, then we need a cryptographic key that can be stored on the chip after fabrication. So we need non-volatile memory. So on these plastic substrates, electrically readable, writable, non-volatile memory does not exist, at least not at the moment. So for example, there's no flash memory. There's two methods for non-volatile storage of some bits, and those are both one-time programmable storage mechanisms. So we can use an additive method where we connect wires with conductive ink, and we can use a modificative method where we cut wires with a laser. And I'll give a few examples. So in the additive method, this is what we could do. So we could connect each bit that we want to store after fabrication. This can be a cryptographic key bit, for example. That's why it says key bit on the slide. We could connect that bit to a logical 0 and to a logical 1 and put an interdigitated finger structure in between. Now we can use conductive ink to choose which key bit would be connected to either the power supply or the ground voltage, to either set the key bit to 1 or to 0. And as you can see, this is a one-time programmable mechanism. Another mechanism is to use a modificative method, where we connect the key bit initially to both the power supply and the ground. Of course, we cannot turn on the power supply before programming the key bits in this case, because here the wires will be cut with a laser, and either we cut the left wire to put the key bit to 1, or we cut the right wire to put the key bit to 0. Okay, so now we had a look at what the advantages are of using the technology, and also which one-time programmable storage mechanisms there are for non-volatile storage. Now let's have a look at hardware security. So to reason about hardware security, I took a very simple symmetric key authentication protocol, which is actually very relevant in the setting that we look at, because if we have a flexible RFID or NFC tag, then it should be possible to read the values of the tag with a reader. And typically these tags are passive, so the reader provides power supply remotely, and then there's data communication between the reader and the flexible tag. Now, if we want some kind of security, we should have, like the simplest form is to have a pre-shared cryptographic key stored on the reader and also stored on the tag. So before deployment, after fabrication, these keys are stored on both devices, and then the flexible tag will go in the field and will be used. The key is there. So this is what we have beforehand. Now, the simplest thing that we should enable is that the reader can authenticate itself to the tag to make sure that only legitimate readers can read out the values from the tag, and that not just anybody can connect to the tag and read out the values. So that's why we have this pre-stored or pre-shared cryptographic key, which will be used now by the reader to show that the reader is legitimate and is authorized to read out the values from the tag. So how can we do this? So how can the reader authenticate itself to the tag? First step in this simple symmetric key authentication protocol is that the tag generates a nonce, RA. And a nonce is a number that is only used once. It is used for freshness in cryptographic protocols, and that's what it also is used for here. So the tag generates a number that is only used once, which means that in a later phase, when the reader has to authenticate itself to the tag again, flexible tag always has to generate another nonce. So it can never be the same value. So the tag generates a nonce RA. The reader then does a computation on this RA. And this computation can be, for example, a MAC. A MAC is a message authentication code, which is a cryptographic function that, let's say, transforms this RA into another value, T1. This can be also, for example, an encryption algorithm. The reader does this using the secret cryptographic key K. So the computation is done. So imagine this being an encryption with a cryptographic key K, and RA is the plain text and T1 is the ciphertext. So the reader sends this T1 to the tag again. And what the tag does is it computes the same, it does the same calculation. So it takes the nonce RA. It also computes the message authentication code or the encryption using the cryptographic key K, and it computes T2. And then the tag compares T1 to T2. And if T1 is equal to T2, then the authentication has passed. So then the reader has authenticated itself to the tag. So this is a super simple symmetric key authentication protocol, and the reader authenticates itself to the tag by actually showing that the reader has the same cryptographic key as the tag. Now, what do we need in terms of hardware security, hardware requirements for security on the flexible tag? That is our challenge. First of all, we need secure key storage. So we need to be able to store the key K on the tag. Second of all, we need to be able to generate a nonce. So we need a nonce generator. And then third thing is we need to be able to compute this MAC or an encryption algorithm. So we need like a digital crypto circuit. Of course, if you have a processor on the tag, you can also do this on the processor. We are assuming here that we don't have a processor on the tag and that this crypto circuit needs to be implemented in a dedicated way on the flexible tag. And now we will have a look at these three things. So first of all, we need a digital crypto circuit to compute the MAC, compute an encryption, like I said, with the secret key K. So I'll present like our first experiments in this direction. First of all, we had to pick like a cryptographic algorithm. We had to, of course, build the digital architecture. Then, we had to choose like which type of standard cells we use and which transistor. So first of all, when we look at the algorithm, we chose to use an algorithm like a super small, or let's say the smallest cryptographic algorithm that does not necessarily provide like a super high level of security, but that could show like that this first experiment is successful and that we can actually do some crypto on it. So we chose for the K1010-32 algorithm, which has been proposed like a bit over a decade ago, which has a block size of 32 bits, which means that plain texts are processed in blocks of 32 bits, and ciphertexts are also generated in blocks of 32 bits. The key size is 80 bits, and the algorithm assumes that the key that is used is burned into the device. This is opposed to other algorithms where the key has to be stored in a register on the device and is updated in every round of the computation, where the key is then replaced by a subkey or a round key that is used in the next round. In this case, we don't need to do that sequential key schedule. We can just have the key burned into the device, and all the subkeys or round keys that we need will be derived directly from this fixed value that is stored in the device. So K1010 is built based on a number of shift registers, a number of logic gates. And this is actually the digital architecture that we provided. So we serialized everything. Also because the number of inputs and outputs on our chip, or the possible number of inputs and outputs is quite limited. So this is the interface we have. We have like the start signal at the input, clock signal, and one plain text bit that is serially provided to the architecture. At the output, we have one ready bit and one ciphertext bit, CT, coming out. And what you can see on the figure is up at the top side is the key schedule. So the key, the 80-bit key, is entered into the key schedule, and then every clock cycle, a new KA and KB bit come out, and these are the bits that form the key stream for the actual encryption algorithm, which then takes in the plain text PT and generates the ciphertext bits CT using KA and KB and some control signals. This is what the standard cells look like that we use. So we have to, since there's only N-type PFTs, we have to use pseudo-CMOS logic. And what you can see on the figure is an AND gate in pseudo-CMOS logic where full die network is repeated twice, and we need a second power rail or power supply, which we call V bias, which has to be at least 2 times the threshold voltage higher than the power supply in order to make sure that we have a rail-to-rail output here at V out. And then the transistor that we use, the N-type transistor, I showed before on one of the previous slides, so I'm not going to repeat that here. And so we did our first experiments. We implemented this algorithm, K1010-32. And as you can see here in this layout picture, it's quite large. It's like 20 millimeters by 20 millimeters, which is of course a lot larger than silicon chips. We can also see at the top where we apply or where we program the 80-bit key that is used, and I will zoom into that later. And at the bottom side, we have like 48 paths, which we do not use all for I/O, for VDD, V-bias, and for the ground. Yeah, and this is all a bit over 4,000 thin film transistors. At that time, this was this is 2 years ago. At that time, this was the largest digital circuit in this technology, but in the meantime, technology has improved a lot. And actually, my co-authors in this paper will show at ISSCC, at the next ISSCC, a circuit of around 16,000 DFTs. So that is what is possible in the meantime. Then, of course, we had to test the chip. So we made a test setup with an FPGA, supplying inputs and checking the outputs of the circuit. And we left the chip on the glass carrier on which it was produced. Of course, for deployment, it needs to be taken off the glass carrier, otherwise it's not flexible. Yes, and in that case, connections. So now we made connections with probe card, and during deployment, connections should be made with for example, silver based. So for these first experiments, we programmed, so through this one-time programmable storage mechanism, which I will also show later, we programmed a fixed 80-bit key. We applied 1,000 plaintext automatically, and we got correct ciphertext for this combination of VDD and VBIAS. So we always chose VBIAS to be like 1.5 times VDD. And this worked at a clock frequency of 10 kilohertz. So if you then take into account that you need 32 bits for shifting in the plaintext and also 32 for shifting out the ciphertext, and that the algorithm for the actual encryption needs 254 cycles, then we get a total latency of almost 32 milliseconds, which is of course a lot, and also a lot larger than on silicon chips. But like I said before, for applications where low cost is super important, and also this flexibility, and where performance or speed is of less importance, this doesn't matter. Okay, so we already took a look at the first thing here, which is the digital crypto circuit. So that was one thing that we needed for our simple symmetric key authentication protocol. The second thing that we need is secure key storage. So we need to be able to store the cryptographic key on the tag. So how can we do that? So like I said before, we can use like a one-time programmable key storage mechanisms. So in general, actually, when you look at key storage mechanisms, then there are one-time programmable key storage mechanisms with fuses or antifuses. There's non-volatile memory like flash, or we can have battery-backed volatile memory using SRAM, for example. In this case, of course, we will not use fuses in the same way as in other technologies. But here we also have one-time programmable mechanisms, either additive, like I showed before with ink, or modificative with the laser. The other technologies are not possible yet. So let's have a look at what we did in our first experiments. So we used the modificative method based on lasering. So this is a small part of our chip where you can see, remember we had 80 key bits at the top. You can see key bits 26 to 36 here. And of course, the others are on the left and on the right. So what we did was we connected each key bit to both the power rail and the ground rail. And then before turning on the chip, we cut with a laser one of those two wires. Yeah, and at the bottom, you can see part of the digital logic. So let us now zoom in to, for example, these two key bits, which is key bit 28 and key bit 29. If we zoom in, we can clearly see that the left key bit is connected to the power rail, which means the key bit is 1, and the right key bit is connected to the ground rail, which means this key bit is 0. So the problem is that these chips are not packaged and that the features are quite large. I remember 20 millimeter by 20 millimeter. So you can easily, at least on a microscope, you can easily read out each key bit. And that is something we don't want in a security setting, of course. We don't want the key bits to be easily read out. So what can we do? So this is a mechanism that we propose to program the key bits in an invisible way. So what we do is we use lasering again, but in this case we do not use lasering to cut wires, but we use lasering to change the temperature in the TFTs, which cause a shift of the threshold voltage. So if you look at this picture here, or at the graph here, then you can see that in the full line, this is the initial state of TFT, where of course the TFT starts conducting when the voltage we apply at the gate is larger than the threshold voltage, which means that if we apply a certain negative voltage V neg at the gate, then the transistor is off. If we now suddenly use a laser to cause this shift of VT, then we get the dashed line. And then with this same negative input voltage, the transistor is suddenly on. So if we use a fixed input voltage, then the TFT switches from off to on after the lasering, or by doing the lasering. So how can we use this for programming the key? So each key bit we connect through a TFT to both the ground rail and the power rail. So the key bit is floating before we do anything. So we are in this state where V neg at the input of the TFT does not cause the TFT to conduct. Before lasering, we have this state. The key bit is floating. Then after lasering, if we change the temperature in the left, or in the, let's say in the TFT that's connected to the ground rail, then suddenly this TFT starts conducting and the key bit is 0. If we do the same thing for the TFT that is connected to the power rail, then the key bit becomes 1. Okay, so the goal was to have an invisible mechanism for key programming. So if we, so of course we went back to the macroscope and checked microscope images to see if it's really invisible. Unfortunately, we could see a difference between a TFT that was lasered and a TFT that was not lasered. So that didn't help them, actually. So then our next solution was to apply different settings of the laser, because different VT shifts that cannot be visually distinguished. So we explored many settings of the laser, where you can see all the blue curves or the status or the IDVG graph before lasering, and the red in red you can see the status after. So then we tried many settings, and we saw that these two connections or these two combinations actually looked quite good. So if we zoom in, then these are the settings that we used. So the setting used in the top image, there we use an attenuation of 45 dB in low energy mode, where we applied 1 pulse with the laser. And in the bottom image, we use second setting, attenuation of 35 dB in low energy mode with 2 pulses. And what you can see here is that the first setting causes the VT to shift significantly, and the second setting does not cause the VT to shift significantly. If we now apply a negative voltage at the gate of -5 volts, then after applying the lasering with the first setting, the transistor or the TFT switches to the on state. And if we do that with the second setting, then after lasering, the TFT does not go to the on state. So we found a solution where we applied lasering in both cases, but the effect is different. And then, of course, you can see it on this slide, sorry. In both cases, you can see that lasering has been done, but at least with the eye, under a microscope, you could not see the difference between a transistor that was lasered with the first setting or with the second setting. Of course, you can argue that you could use more advanced techniques to see the difference, but this was our first experiment, and more research is definitely needed. Another way that we didn't really explore yet to prevent the readout of secret key bits is to use ink. So actually then we could use any method that would normally be where it would normally be visible to which bit the key is programmed. But if we then cover the key bits or the programming of the key bits with ink, at the top and at the bottom of the chip, because we can look at the circuit on both sides. Then we could also probably cover, make it invisible to which bits the key has been programmed. So the ink should then be, of course, non-conductive, because it would otherwise disrupt the whole circuit behavior. It should be non-transparent, because it should help us hiding the key bits. And we should also make sure that it's not soluble, because then an attacker could just remove the ink. But this is something we still need to explore. So we had a look at key storage mechanisms, because that's what we needed for our simple authentication protocol. And what we did was we used the laser approach, and we also found a solution for making sure that key bits are not visible under a microscope. Now there's other ways to store a key or to program a key into a device. And another method is to use a physically unclonable function, or a PUF. This is something that we still need to explore in this technology, but I still want to give you a view on what the challenges are. So the difference with traditional key storage mechanisms is that a PUF does not store the key, but generates a key. So the keys are only generated when needed, and the keys are only there when we turn on the power supply. Now, what does a PUF look like? So a PUF uses process variation for device unique key generation or for device authentication. Now, as you can see on the figure on the left, if we have two chips where we implement the exact same circuit to which we apply an input value to this sub-circuit, which we call the challenge, then because of process variation, one chip will generate a different response than the other chip. So by applying the same challenge, we get different responses on both chips because of process variation. So PUFs are circuits that make use of process variation to make sure that each chip that holds like the same PUF circuit generates a different response. And this can be used for authentication. For authentication, it can be used when we have like multiple challenge response pairs stored in a database, such that an authentication server, for example, can send a challenge to a chip and check if the response that comes back is correct. And this way the chip authenticated itself. Or we can also use it for key generation, where we typically have a very limited number of challenge response pairs that we use, or only one even, where we just have one key that is then device specific. So how does it work for authentication and also, so for authentication. So first we have an enrollment phase that is done offline, where the database server sends many challenges one by one to a chip that holds a PUF. The PUF then responds with the value R or X here in the figure, which is then the response to this specific challenge. And the database server stores all these challenge response pairs. Then in the online phase, where the chip is deployed and is somewhere remotely being used, then the database server remotely sends a challenge to the chip. The chip responds to this, and the database server checks, or the authentication server checks, if the response is correct or not, because in the offline phase, it stored all these challenge response pairs beforehand. And since the response is different for each different chip, a chip can authenticate, or a device can authenticate itself through this mechanism. Now, when we want to use it, in our case, in the simple authentication protocol, if we want to use a PUF for key generation or key storage, then there will not be a large database with challenge response pairs. We could either choose to have a few keys, so a few challenge response pairs, or only one, where there's just always a fixed key generated by the device. But this key is then again device unique, so different for each chip that we build. Now, what are the challenges here? So first we have to look at the properties of PUFs, or the desired properties of PUFs. They should be it should be easy to evaluate the puff. So when we send a challenge to a puff, the circuit, it should be easy to generate a response. So for example, the response should be generated relatively fast, and so the puff should not be too slow, for example. Uniqueness is important, of course. When we have two chips, then they should generate a different response to the same challenge. Then reproducibility or reliability is important, and this is something that is always checked when, for example, a new puff circuit is proposed. So under different operating conditions, such as temperature, supply voltage, the puff should always generate a reliable result. And actually, typically some post-processing is needed after. So the result is not always exactly the same, or the response, but by using post-processing, we can always make sure that we have a reliable process. Then, of course, unclonability. It should not be possible for an attacker to generate a circuit that generates the same responses to the same challenges. Unpredictability. So an attacker should not be able to predict the next response to a certain challenge, and this is actually a problem because in many puff circuits, it has been shown that by using machine learning to model the behavior of the puff, this unpredictability requirement does actually not hold. It should also be a one-way function, so you should not. It should be the case that you cannot go back from the response to the challenge, and there should be tamper evidence. So if somebody tampers with the circuit, this should be visible in the response that the puff gives. Now, what is a challenge that is specific for key generation with puffs on flexible foil? The thing that we need to explore is that digital circuits continue to operate correctly when they are bended or stretched. But we don't know if a puff still produces a reliable and unique output when bended or stretched. So I already said that we have to evaluate the reliability of the puff under different temperature and supply voltage conditions. But of course, when we bend or stretch the circuit or the chip, we should also check if the puff response is still reliable. And that is something that still needs to be explored. Okay, so now we go back to our simple symmetric key authentication protocol. So we showed first that we can have like a very simple digital crypto circuit, the K1010 algorithm we implemented. We also showed our method with lasering that to some extent makes the key bits that are programmed invisible. And now the third thing that we need is a nonce. So nonce was a number that is only used once. So how are nonces generated? So to generate a nonce, we either need a true random number generator, because when we have a true random number generator, then we know, if it's truly random, then we can assume that the chances are not very high that the same number is generated twice. Another option is to use non-volatile storage, where we use, for example, a counter or a linear shift feedback register to generate new nonces every time. But then when the circuit is powered off and powered on again, we need to make sure that we don't start every time with the same value again, because then there would not be freshness and we would generate the same value again, which would not be a nonce. So in that case, we would need non-volatile storage to keep track of which nonces or which values have been used before. Now, electrically readable and writable non-volatile memory does not yet exist in the considered technology, so we cannot do that. So the other option is to have a true random number generator. But there, this still needs to be explored actually, so that's also still open. Because when we build true random number generators, then many of these true random number generators are using or based on metastability, which is an effect that we use in the design of TRNGs. But when we use pseudo-CMOS gates, everything might become different. because the input-output characteristic of pseudo CMOS inverter, for example, is a lot different from CMOS inverter. So this is something we need to check because it might be the case that we get a lot of bias in the random numbers that are generated, which makes it more difficult to really have randomness, and that's something that we need to explore. So another challenge to be tackled. So in conclusion, the technology of digital circuits on plastic substrates, so flexible electronics, is rapidly improving and soon ready for mainstream applications. And there's, like I said, already technology available commercially now. So when we did our experiments, that was still in-house with my colleagues at IMEC. But it's crucial to guarantee the security of these applications. And we already tackled a number of challenges, but there's many more challenges to be tackled. For example, if we want to make our system compliant to NFC standards, then the delay of the authentication protocol needs to be within certain bounds. And that's something that we didn't completely check yet. Also, if we want mutual authentication, where it's not only the reader that authenticates to the tag, but also the tag that authenticates to the reader, yeah, then it takes even longer. So that then it becomes even more difficult. Also, like a few decades ago, there was a lot of research on putting public key cryptography on RFID tags. We could also have a look at public key cryptography in this technology, but that would require even more TFTs or transistors. So it's not sure that we will manage to do this, but this is another challenge to be taken. So I'm very excited about this research, and since the technology is now also commercially available, I think a lot more can be done. So yeah, I invite you to also have a look at it and to contribute to the security of these chips. Thanks a lot.